All right, y'all. Sorry about that. I got out of my screen for a moment. This worksheet goes along with the last worksheet we just did on basic reaction rates. So again, I'm giving you a little video because I'm going to be out of town at a conference, or if you're homesick, you can still do this. Now, in the last worksheet, we focused solely on finding the rate of change of reactants or products. In this worksheet, we're going to go from one of the chemical species to the whole reaction. So let's start off with just reviewing. How do you find the rate of consumption of a reactant? Consumption just means it's being used up. You guys know this. It's change in concentration over change in time. Do you see that negative sign there? Why is that? Well, they said it's being consumed. It is implied that the rate will be negative. So you don't have to put the negative sign in there. But the reason really they put that negative sign in there is so that you can take the rate of a chemical and turn it into the reaction rate for the overall reaction. See, overall reaction rates are always positive. But you guys know that reactants will always be negative because they're being used up. So my point is that if you're looking for the rate of consumption, you don't have to worry about it being a negative. You can just give me the value. So you should be able to do these pretty easily, okay? These are not terribly hard. By now, you should know what the triangle means and what the brackets mean. I've explained that. And then again, the purpose of the negative sign is to turn it into positive so that we can go to a reaction rate, all right? And by the way, it says provide an analogous equation to the rate of production of a product. Well, isn't it going to be the same exact thing, except it's going to be the change in concentration of the product divided by the change in time? And you don't need the negative sign because they're always positive. So number 4 is basically the same thing as right there. All right. So in this model, we're going to go from different reactants and products to the overall reaction. Okay. So here's our reaction. Very important you pay attention to it because those coefficients are going to come in handy. And they were also sneaky on this one. So the reaction described in equation 2 was carried out in a 2-liter solution. Why is that important? Well, they only gave you moles. And you guys know that you need concentration. How do you find concentration? It's moles divided by liters, all right? So the first thing we're going to do is focus on moles. But down below, to actually do the math, we're going to have to convert things into concentration. So number 1 says fill in the missing things. Well, if at time 0, all you have is this and no products, how many of these did you make? You have to do a little detective work, okay? In 100 seconds, how much did this go down? Well, if you subtract, you get 0.60, right? And now you have to do a mole ratio. Every time you use 3 of these, you make 2 of those. So if you do a mole ratio, remember this goes on the bottom so they cross off. Let's go to the moles of Cl negative. The numbers come from the equation. 0.6 times 2 is going to be 1.2 divided by 3. You're going to get 0.40, right? So do the same thing to get the moles here. Take either this or this and do a mole ratio to get that, all right? Now you've got all your moles. Number 6 wants you to actually find the rate of change, and that is going to be concentration over time. Y'all, you do not have concentration. You have moles. So you need to divide all of these numbers right here. That's the 0.6, the 0.4, and whatever. You need to take those values, not the 1.8, the 0.6, because that's what changed, and you need to turn it into concentration. So you just have to divide each one by 2. That's it, okay? So get your 3 rates of consumptions and productions, all right? The number 7 says, based on the answers above, what is the rate of the reaction in the model? This is where you want to come back and read this little thing here. Sorry about that, okay? The rate of a reaction is defined as the rate of consumption of a reactant or the rate of production whose stoichiometric coefficient is 1 in the balanced equation. What does that mean? Go back to the equation. If somebody in this equation, let me erase this for a second. If somebody in this equation has a coefficient of 1, Whatever its rate is the rate for the entire reaction. So you already found that, right? ClO negative, you found it right there. Nope, I lied. ClO3. You already found it. So that is the rate for the reaction, all right? Can you take the other two rates and get the rate of the reaction? Yes, you can. All you have to do is divide by the coefficient. So whatever you got for ClO negative, divide it by 3. Whatever you got for Cl negative, divide it by 2. So how do you go from the rate of a chemical to the overall reaction? Just divide it by its coefficient. But if you already have a coefficient of 1, there's your answer, okay? And that's what 9 and 10 is getting into. Divide it by the coefficient. It is that easy. All right, then 1 through 4, make sure you show your work, is just practicing this. All right, give it a try. There's nothing tricky here, but just pay attention to all the things it's asking you to do. So like number 1, is it true or false? And explain. So don't just tell me true or false, explain. Number 2, for this reaction, they give you this. They want you to find that. And then they want you to find the overall for the whole reaction. Again, on this one, they give you O2, find O3, and then find the rate for the overall reaction. So remember, you just have to divide by a coefficient. Now on this one, they give you water. You're going to find the rate for all the others plus the reaction. So 5 answers on this one. All right, give it a try. Check your answers. They're at the front of the room. Good luck.